Well, we are going to finish up this example from the last lecture. You may recall that the last lecture, 5.1, was design stage uncertainty analysis, because I sure did. So you may also remember that. So we have an example that I find kind of charming. So let's do that. Force measurement with a load and a digital voltage measurement. So we want to estimate the design stage uncertainty. What was that again? Design stage uncertainty? It's our estimate of how uncertain we will be in our measurement before we ever make any measurements, right? It's like we're designing a measurement system. We want to get an idea roughly of how much confidence we're going to have in a given measurement. But we've never actually tested it. We've never actually taken any data. We haven't seen how much the data varies when we actually measure it yet. So we don't have a full estimate yet. But we're trying to get an idea because, it is nice to be able to predict roughly what your at least the lower bound is on your uncertainty from the data sheets of the instruments you're going to use. Because it's probably not going to be any better than that. It might get worse than that, but it's probably not going to get any better than that. So, estimate the design stage uncertainty for the measurement of a force with a load cell, including amplifier, so they're not going to break that part out like we did in the midterm, that transduces force to voltage, and a digital voltage measurement via an analog input of a microcontroller. The following tables include specs from each instrument's manual. So, the load cell, let's say it has a range from 0 to 60 newtons. It has a sensitivity of 0.1 volts per newton. So if you put in 10 volts, if you put in 10 newtons, you should get about a volt out, right? And linearity error is 0.15 millivolts per newton, sensitivity 0.25 millivolts per newton. And so that's for the load cell. And then we're also going to have a microcontroller. If you see this mu c, that means microcontroller. Also, because the internets don't really use LaTeX as much as they should, you'll see UC a lot, which also means microcontroller. It's just that they don't have this part because it's pretty weak sauce. And this abbreviation, AI, doesn't mean artificial intelligence. Sadly. It would be cool if it did, but we could talk about artificial intelligence sometime too. AI, though, in this case, means analog input, okay, to the microcontroller. So a microcontroller that you might do some prototyping with and is cheap and fun and I recommend would be like an Arduino, right? That's a microcontroller that has analog inputs to it, so you can measure analog voltages coming in. So it has the following specs, this analog input. It has a range from 0 to 5 volts, an analog to digital conversion resolution of 12 bits, we'll talk more about that, and an absolute accuracy of 50 millivolts. So those are common specs. I don't remember, I pulled these from some microcontroller. I think it was the MyRio, maybe, analog input. Anyways, I pulled them from some microcontroller spec sheet because I thought I should get realistic values. So say we were doing this, and then maybe we needed to do something with that, right? So the reason you'd use a microcontroller is not to necessarily get the reading. You might do it to get the reading, but also there's probably something else involved too. Like maybe when the load cell sees some input, you want to do something, right? So the microcontroller would be monitoring this load cell to see, do I need to do anything? Checking that measurement. So we want to We want to estimate the design stage uncertainty for measuring a force with this setup.
I already see an issue with this, though.
What's the issue?
Once it gets over 50 newtons input,
Yeah.
you're not going to read anything.
That's a good point. So, our range for our analog input is 0 to 5 volts, but the range on the load cell goes up to 60 newtons, but the sensitivity is 0.1 volt per newton, so you could end up putting 6 volts, up to 6 volts, into this analog input. So, there are different ways of dealing with that. The quick and dirty way is to just voltage divider it down, which is totally fine because you are using very high input impedance stuff here, so it's not going to draw any current really. And so probably you're going to just use a voltage divider here. The voltage divider, it doesn't have to divide it down much, right? Just a little bit. It's only 20% over the range, so divide down a little bit. Or you could just say, well, we're not going to use it above this voltage. Oftentimes, these analog inputs on a microcontroller are not so sensitive that they're going to get damaged if you go above some reasonable amount. If you go above a lot, then they'll get damaged. But if you go above a little bit like that, usually it'll stop giving you, it'll just give you 5 volts. Like if you it's called saturating it. It'll just give you 5 volts if you're over 5 volts. People also call it clipping too, where like it'll look like your signal will be going up, 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 and then you like leave the range and it just like flatlines. It says 5, but probably it's 6 or 7 or something.
That was happening in our instrumentation lab where we're trying to measure something else and it goes off with its balcony.
Yeah, and that's, undesirable behavior. It's not always something that you can mitigate that. So when you're doing a measurement, you like to avoid it, obviously. Something that when we start doing control, that happens is that your control output you have tied to some control law, which depends on the measurement. Well, sometimes you're going to measure something. It's like, oh, you're like way off in your error, and so you want to put out some like large control actuation force. Let's say, like, say you're trying to balance something, and it's getting way off, and like you want to put this huge force to counteract that. Well, maybe your actuator doesn't actually have the ability to put that much out. So that's also called saturating. It's saturating your actuator. And so it happens a lot. Sometimes it happens in a sort of benign way, and it's not too bad. It isn't a big deal. Other times it can be an issue. And in analysis, it's tough to deal with because it's very nonlinear. So if you have to do simulation when you might have that happen, the saturation happen, then it makes it tougher to simulate. But totally possible, and I hope to one day go through that with you guys. So this is so much I have to teach you. So much. So excited. Okay. Good. So so this setup, I mean, as was pointed out, it's not perfect as it is, and we probably would need to do some things to make it a little bit better. Like we should probably divide down that with a voltage divider. In which case, it would be totally fine. We would then go for 0 to 5 volts with our load, but we would have to multiply our voltage that we get by this factor, this voltage divider. We should undivide it, right? Multiply it back up so that it is the correct value. So we just have to be careful. Okay, so we could estimate the entire design stage uncertainty in one RSS value. But instead what we're going to do, because RSS value, so what we're going to do is the root sum square estimate of the design stage uncertainty of the load cell, and then we're going to do it separately for the microcontroller, and then we're going to combine them together. Because we said that the RSS method works, it works not just for a measurement from one instrument, but it also works from uncertainties that come from multiple concatenated instruments. When you do one output goes into the next input, etc. When you concatenate these devices, you can do the same thing. So you can just lump all of the uncertainties together into one big RSS. Mathematically, it's equivalent, but it's useful to go through and see like what is the load cell's uncertainty versus the microcontrollers, and see which one's dominating and that type of thing. So we're going to do one for each and sort of break it down, if you will. Note that the errors depend on the magnitude of the measure n. So if your linearity and sensitivity errors here are given per Newton, right? So this is a very common thing. It depends. Sometimes it's given an absolute thing. So maybe your linearity error will be 0.15 millivolts, just period, okay? But sometimes it's given per Newton, and you need to recognize that and to say, okay, we'll estimate the uncertainty for maybe some nominal measurement of force. So maybe in your application, you're going to be hanging out around 30 newtons most of the time or something like that, or you want to make sure that's a really good measurement at 30 newtons. Maybe you estimate it on that. Or what we're going to do in this case is say, let's take worst case scenario. Worst case scenario, we're up at 60 newtons, right? Because that's the biggest error that we could get. 60 newtons times 0.15 millivolts per Newton. So let's assume that's the situation, and let's do the design stage uncertainty. Remember that the design stage uncertainty also includes the accuracy estimate, right? The accuracy of the device is there's the so-called zero order uncertainty, right? U0. So for load cell, not given, right? We have no accuracy information. We have range, sensitivity, linearity, and sensitivity errors, but we don't have the accuracy or we don't know any sort of like readout values for like how many digits that are given, nothing like that. It's analog, and it doesn't give us any accuracy value. So we just have to ignore it. We just don't have an estimate. It's not that it's necessarily small. Probably it's small if they don't give it and they give this other information, but it's hard to say. But we can still find U design. So let's do that. So U design for the load cell equals, so we're going to use the root sum square. We have two given error values from the spec sheet, right? So that's two different uncertainty sources. So two sources of uncertainty. So we're going to use the RSS of that, and we're gonna need to know the uncertainty we want the maximum one, right? We decided we would use, since it wasn't given, we didn't have an operating point for a specific force that we wanted to worry about. We're going to use the highest, so 60 newtons. So we're going to use 60 times, so we'll do linearity error first, times 0.15. So that is the uncertainty in millivolts. It's important to recognize the sign here. In millivolts of the unit here, in millivolts of the linearity of this instrument. So we combine it with the sensitivity, which also is per Newton. So let's go with the biggest, which is 60 newtons, times 0.25 squared. And what I got was 17.5 millivolts. So that's our uncertainty, our design stage uncertainty for the load cell measurement. Okay. Notice that this is in voltage, in terms of voltage, right? But when we're estimating the uncertainty in a measurement, although we almost always will work with voltage for a measurement because it's almost always what our readout is in voltage. We almost always care about the original quantity. Unless we're measuring voltage, that's not voltage, right? So it's force in this case. We want to know the uncertainty in the force measurement because that's what we're measuring. We're measuring 0 to 60 newtons of force from the load cell. So we want to know what this uncertainty means for our force measurement. So let's convert it. When we can convert it through this sensitivity value here. So the sensitivity tells us how to convert for that load cell from a voltage to a force, or vice versa. So in terms of force, the design stage uncertainty for the load cell is equal to 17.5 millivolts, so times 10 to the minus 3 volts, times 0.1, well, no, not times. Times would be wrong, divided by 0.1 volts per newton to give us newtons, right? So divided by 0.1, which gives us 0.175 newtons. So that is our design stage uncertainty in terms of force for the load cell. What confidence do we have in this? 95%, because it wasn't stated in the spec sheet what these values were associated with in terms of probability. So we assume that it's a 2 standard deviation normal distribution and that there's a 95% probability it'll be in that range. Plus or minus this. Okay. I think that one of my favorite sayings applies here. Often wrong, but never in doubt. That's what we are. We just pull these numbers out of a manual and just kind of mash them together with a formula that just kind of comes to us because it's just a formula that seems okay. Yes. How confident are we? 95%. So, yes. Okay. So now the microcontroller's analog input AI has these specs associated with it. It performs analog to digital conversion. Okay, so it has an analog input, but it's going to represent that analog voltage value, which is continuous, right? From 0 to 5 volts. If you had all of the real numbers in between, there's an infinite number of real numbers in between 0 and 5, right? Technically, an analog signal could take on any value in that entire range. Digitally, we can't represent all that, right? We can only represent it to a certain approximation in terms of a floating point number. So the resolution that we have on that digital side affects the measurements. Okay. So it performs an analog to digital conversion with resolution of 12 bits, and so you essentially have 12 bits. So a bit is either a 0 or a 1 value. So you could think of it as representing a number in binary. So if you have 12 of them, you only have a certain number of distinct values that you can assign if you have 12 zeros and ones in binary to represent it. That's limited number that you can represent. And so a 12-bit, so if you have more bits, you have more values you can assign. So 12-bit is a pretty common one to use. It's not like super high resolution though. but it's not bad. So 12 bits over 5 volts. An n-bit resolution analog to digital conversion over a range R gives resolution, so AD conversion resolution over range R with n bits has resolution in terms of, so has resolution, a little bit redundant there, has resolution R divided by 2 raised to the n power. So essentially you're dividing your range by the number of possible binary numbers you can represent in 12 bits. And of course you can convert a binary number to a base 10 number as well, so it represents just floating point numbers, right? So those are the possible, this is the resolution we have because that is the sort of the step size we can use to divide up that range from 0 to 5 volts. So, so our uncertainty, so our zero order uncertainty, zero order is, for the microcontroller, in terms of voltage, is 1/2 times 5 divided by 2 to the 12. So this is our, we've essentially converted this to an analog resolution, right, as a range of 5 volts divided into 2 to the 12 different values. 4,096 possible voltage levels between 0 and 5 volts. It's not bad, right? And we divide that by 2, and that gives us our a zero order uncertainty, which, let's see, I did compute that somewhere, 610 microvolts. So we can combine this, go to the next page. We can combine this combined with the absolute uncertainty. So absolute uncertainty is given in the manual as well, not just the resolution. So the absolute uncertainty was just given as a straight 50 millivolts, right? So we don't have to do anything to that. It's just 50 millivolts. So we have ourselves U design for the microcontroller. In terms of voltage, equals square root of 0.610 in millivolts squared plus 50 in millivolts squared, which, notice that 50 is much larger than 0.6, and within the significant digits we're working with, this is just 50 millivolts. So in other words, absolute error is dominant in this case. So we didn't need more resolution, that isn't really the problem here. We just have this absolute uncertainty. And that's coming from the fact that each of these analog inputs, 50 millivolts isn't an insignificant amount of voltage. It's difficult for them to guarantee you, when they ship all these things, that you're going to be more accurate than 50 millivolts. They try to calibrate them as well as they can and manufacture them as well as they can to be within that, but that's all as good as they are. So these things aren't great for like high precision voltage measurements. They're okay for some voltage measurements, but high precision, they're not. They're more made for being inexpensive and able to do lots of things. So, all right, some high-end ones can do, but it seems like you have very diminishing returns. You spend way more money and you get like a little bit more resolution, a little bit more accuracy. Okay. So we want to turn this into a force sensitivity or a force uncertainty as well. So in terms of force, we have to use the transducer's conversion again, right? The sensitivity of the transducer that converts the force into a voltage. So we're going to say UD mu C F in terms of force is equal to, so our 50 millivolts, 0.050 volts divided by 0.1 volts per Newton gives us a half Newton. Okay? So half Newton of uncertainty coming from the microcontroller, and let's see, what did we have for LC? We had, what is that, a sixth? Is 0.175 a sixth? Oh, not exactly. Yeah, no, it can't be. I don't know. 0.175 seems familiar to me. In any case, 0.175 newtons from the load cell. So, guess what we're going to do to combine them? RSS again. Because that's all we know how to do. So we just keep using it. You know what they say? For a hammer, everything looks like a nail. So,
Have I heard that twice today?
Yeah, I was just thinking.
who told you that?
Einstein.
No.
Yeah.
We're on the same wavelength. Our offices are next to each other. We've synchronized.
7 divided by 40 is 4.175, but I feel like that's very obscure.
I think that's it. Yeah, I once divided 7 by 40. Okay, I'm going to digress for just a moment. Do you know, it's really interesting. There's a pattern in human behavior that makes certain numbers very significant, okay? And I have known people who are obsessed with the number 7, obsessed with the numbers 5 and 7 in combination. There's like a whole cult around 5 and 7 together or something. Yeah, yeah. And then also 40, 7 is clearly a pretty, common number to have a lot of things show up as, especially in our weeks and all that. And lucky number 7 and jackpots and all that. But the 40 is also, and I kind of grew up in a bit of a sort of conservative evangelical home, let's call it. And you'll see literature flow past you that has phrases in it like a spiritually significant amount of time.
Are you talking about Rick Warren's purpose-driven, like
40 days
40 days of purpose. Yeah.
is a spiritually significant number of days.
Maybe they were going for 7 days in a week, 40 days, 0.175.
I think that what the calculation there is
I love Aaron's math.
how what division of a week is a spiritually significant division, and 0.175 of a week is apparently that number.
I think you're overanalyzing this.
So how many hours is that?
I don't know, but also 0.175. What, 7 and 5?
I thought you said 5 7.
Yeah, those together. They just when they're together, it's like a power number or something. I don't know. I like hear these things. I try not to listen to these things, but they just stick in my mind, and I can't get them out after they're used.
I wish that was true about my classes.
Yeah. Yeah. You'll remember that though. You'll remember that
That's the only
part.
thing I remember was translation with Dr. Rico.
Yeah.
Only thing I took away from it is 7 and 40.
Coincidentally, those numbers add up to B12. The 5s of Israel. So how do I go there?
What? Oh my gosh.
Oh,
We're on to something
Oh,
here.
no. This is
There's
not
a
the first
code.
Time, this is not the first time I've heard this theory, so.
It's a thing. I don't know. I have had drinks with a person who thought that this was the whole thing, and I think it's fun to talk about.
I think it's for people with too much time.
That's possibly true. Okay, so we have ourselves another RSS opportunity. I know. So let's combine the 0.50 uncertainty that we got from the microcontroller with the 0.175 that we got from the load cell using good old RSS. And we'll get, according to my calculations, 0.53. I know, I think we should probably check because it probably is a 7 and I screwed up. So 95% confidence in that value for the uncertainty, which assumes 95% because no probabilities were given in the instrument specs. So that is the design stage uncertainty. So like all these problems, and like so your homework's got your homework. Do you guys have homework for this chapter yet? No. I'll assign that.
No, we
I don't
don't.
know.
And you won't. As a matter of fact, because I'll say 5 and 7 or something else.
What was the last homework? Wasn't it 7?
Just keep thinking about that.
So only 5 more.
With the average being.
So let's. I didn't hear it.
Darn it, Aaron.
So this is a pretty it's a pretty easy procedure. You got to be a little bit careful, and a lot of it comes down to understanding what's in the spec sheet and what it means, its significance, and then how to use that. Okay, so try to be cautious as you use this method, but recognize that it is rather imprecise, and you're just trying to get an estimate for something. All right, that is. Yeah. Any questions on this example?